Hi, good morning, everyone. Welcome to the last week of the semester. I appreciate you hanging in there. I hope you're doing well and staying safe. Today, we're going to start talking about the final chapter of the semester. We've talked a lot about where we can find life in the solar system thus far. The inner solar system, the outer solar system, Mars, and the moons of the outer planets. And now we're going to shift our focus to looking for life elsewhere in the universe. And so this would be looking for life on planets around other stars. So the first thing we need to talk about are other stars. What types of stars would be the best to find habitable planets around? So we're going to begin that discussion today. And then we will talk about other exoplanets and how we find them and what types of exoplanets we found. So let's go ahead and begin. Here's a question for you, talking about different types of stars and which ones are enriched in heavy metals or in astronomy, heavy elements, or in astronomy what we call metals. So take a moment to think about this on your own. Go ahead and push pause. All right, it turns out the correct answer here is the youngest later generations of stars have more heavy elements. Now these heavy elements are important. These are anything heavier than hydrogen or helium. And so these are the building blocks of life: carbon, oxygen, calcium, iron, all of those things we need to survive. So we can think back here, and we have the tools to answer this question. If you remember back towards the beginning of the semester, we said that in the Big Bang, only hydrogen and helium were created. So the Big Bang created only hydrogen and helium, and all other elements were made inside stars or supernovae, which are the results of giant stars dying. And so what we're thinking about here is the more generations of stars we have, we're going to get more heavy elements. And the thought process being that the more heavy elements we have, the more likely we are to find life. There'll be more planets formed and more chances for life. Okay? Now, I will say that these last two are a bit of an assumption. We have definitely answered this one a little bit, but the last one really, is there more life where there's more planets? We don't really know the answer to that question, but that would be a good place to start. So if we're looking around stars, we don't want to look too far out in the universe. Remember, the farther out we look, the farther back in time we're looking. And so those would be the first earliest generations of stars. They wouldn't have very many heavy elements in them. And as we look closer and closer to the Earth, we're looking more and more into the future. Well, not into the future, but closer to the present. And so those stars would have more elements. So let's look at a little picture of this. This is often referred to as stellar enrichment. So if you look here, this is a star-forming nebula. Remember our nebular theory for star formation. That's where stars are formed. And we basically have two types of stars: sun-like stars and massive stars. So sun-like stars are smaller, but regardless, as they go through their life cycle, they go around, they become planetary nebula, they're creating hydrogen, and so they're making heavy elements here. And same with here, during their main sequence phase. We'll talk about the life cycle of a star in a minute, but we call this the main sequence. And these stars form, and then at some point, they either go supernova or they turn into a planetary nebula. And the heavy elements that they were made are recycled back into new star-forming nebula where newer generations of stars are formed. So this is often called cosmic recycling, where we have basically old material being turned into new material. And as we get more and more generations of stars, we get enrichment in heavy elements. Okay? So again, kind of big picture, the stars are formed in these star-forming nebula, these giant clouds of gas, and then the stars live their lives, turning light elements into heavy elements, and then they die, and they put those heavy elements back into new star-forming regions for newer generations of stars to form out of. All right. So, talking about stars and their life cycles, what one major difference among stars, or basically the major differences among stars, is due to what property? So what single property really defines a star? Again, push pause, think about this for a moment on your own. All right, it turns out the correct answer here is mass. So the mass of the star, this controls everything about a star. It controls its temperature. It controls how big it is. It controls its lifetime, how long it can live. It controls its life cycle, which path it takes. So basically every property about a star, maybe other than chemical composition, that depends on where it was born, but every other major difference of a star is determined by its mass. It's the one key defining feature. And so these different masses of stars, we break into different spectral types, we call this. And the sequence here is OBAFGKM. Now that has some historical significance. They used to be in alphabetical order, and then as we learned more about stars, we rearranged them in this fashion that ranks them from most to least massive. So O are the largest, most massive stars. You can see that down here in the table. So these O stars are like 60 up to 80 to roughly 100 solar masses. And then as we go down, BAFGKM, we get smaller and smaller masses here. Okay, and so it's this column that's really defining all of these other characteristics, the temperature, the luminosity, the lifetime. So color here, this is directly related to temperature. These, ones up here are blue, and then yellow and red. So the color signifies the temperature. Luminosity, this is a fancy word for brightness, how bright these things are. So that's just a little terminology. Now I do have one mnemonic to help you remember this sequence of stellar types. And this can be written out as O, B, A, fine, guy, gal, and kiss me. And we can see here in the first letter, O, B, A, F, G, K, M. O, B, A, fine, guy or gal, and kiss me. So if you're having trouble remembering this sequence, that's always worked for me. All right, let's look at these in just a little bit more detail. I just talked about the colors, the hottest ones being blue, the coldest ones being red. And this goes back to that spectrum, the continuous spectrum, the black body we talked about back when we talked about radiation for a little bit. It's directly related to that. So if you look at the visible part of the spectrum, you see it goes from red to blue. The stars follow that exact same sequence from red to blue. Now we can also see that this has them ordered from least to most to least luminous. So as we go that way, these get dimmer as we go down. These get cooler as we go down. Most to least massive, we talked about that. So these are smaller. And now the couple of properties here that are a little bit backwards from those. So these have gotten cooler, dimmer, smaller. These actually live longer as we get to smaller stars. It turns out that stars are a little bit like vehicles. The bigger the star is like a big vehicle that guzzles lots of gas and runs out of fuel quickly. And a very small star is like a little Prius. It's tiny, but it's very fuel efficient, and it can run for hundreds of billions of years on its gas tank. One thing I want you to notice here is look how short these lifetimes are for the longest star, or for the biggest stars. They don't even live a million years. So these are very short. These are shorter than geologic timescales. And the smallest stars can live upwards of 600 billion years, so many times the age of the universe. So there's a huge range here. Maybe factor of 1,000,000 difference in how long these stars can live. And the last thing I want you to look at is their abundances, how many of these there are. You can see that these smallest stars make up roughly 90% of the stars in the universe. So the big stars are impressive, but there's not very many of them. You can see roughly less than 1% for those biggest ones. And if we include the A's, about 1%. So that's some breakdown of these different types of stars and the classification system we use. Just so you're aware, the sun is right here. It's what's known as a G5 type of star. So the sun is a G star. It fits right into this category right here. All right. Just a little bit more about the life cycles of stars. This is similar to the picture that we saw before. Some things I want to point out is, again, this part is called the main sequence. So the stars are born, and then they transition into the main sequence. They spend about 90% of their life here in this part. And this is where they're burning hydrogen and helium and some other light elements into heavy elements. As soon as they run out of fuel, then they move off of the main sequence and they become a red giant. So then they move into their old age. They either become a red giant or a red supergiant, depending on how big they are. And then they can turn into a planetary nebula. That's what our sun will be. It will have a white dwarf down at the center. Eventually that will cool into a black dwarf. The largest stars will go supernova. Some of those will turn into neutron stars. Some of them will turn into black holes. Those may eventually turn into pulsars or whatnot. Here you can see all of these stellar types turn into big clouds of gas. They either send off their, and even here, they either slough off their outer layers slowly or they explode violently. But this is where they recycle material back into the galaxy. Okay? And these different paths are all determined by the mass of the star. So it's a little hard to see down here, but these brown dwarfs, these are failed stars. Those are less than about 1/10 of the mass of the sun. Low mass stars are everything up to about less than 8 times the mass of the sun. And these massive stars are things greater than 8 times the mass of the sun. And so these different lifetimes, these different trajectories are all determined by their lifetimes, with the smallest ones ending up as white dwarfs, planetary nebula with a white dwarf, and the largest ones, supernova with black hole or neutron star. The intermediate ones will become neutron stars, and the largest ones will become black holes. All right, so that's just a quick look at their lifetimes. So, if we're thinking about these different stars, now that we've talked about what different types exist, how they live their lives, how we can classify them, what types of star characteristics limit the types of star systems that could host habitable planets? So which of these types of stars should we look for to find habitable planets? So please push pause, take a moment to think about this on your own. All right, so it turns out that the correct answer here is all of the above. We need all of these things in order for a planet, or rather I should say for a star, to be a good candidate to host a habitable planet. So it must be metal rich. We need building blocks for the planet itself. We need building blocks for life that may exist on that planet. But we need stuff to build the planets out of. It must last long enough for life to emerge and evolve. Remember when we talked about evolution, it looked like life emerged very quickly, but it didn't evolve for hundreds of millions or billions of years. And it took roughly 3 billion years for us to evolve. It needs to have a stable habitable zone. So it doesn't just need to exist for a long time. It needs to have a habitable zone that isn't changing too quickly. We talked about the evolution of the habitable zone, I believe, last time. And so we need that to be fairly stable. Also, the orbits of the planets need to be stable and nearly circular. We had a brief discussion about Mars and how it has a very eccentric orbit and how that is bad for climate stability on Mars. So we need these planets to have stable orbits. This is particularly important in planets around multiple star systems. So binaries, triple star systems. We'll talk about that more in a bit. So let's go through the different star types and see which ones fit these characteristics. So first we'll talk about massive stars. And by massive, I mean stars that are about greater than 8 times the mass of the sun. So these O and Bs, they only live for about 1 million to 1 billion years. Even less than that. The A and Fs last only for about 1 billion years. So this was insufficient time for intelligent life. So the problem with these two is their lifetimes are too short. They do have big habitable zones. But they're evolving quickly And so not only does the star just not exist for very long, but since the star is going through its lifetime very shortly, the habitable zone will evolve very rapidly as well. They also have copious amounts of ultraviolet light. These brighter, hotter stars not only are more blue, but they have lots of ultraviolet. And remember when we talked about life before the ozone layer was around, Earth had more ultraviolet, and so it was a much more dangerous and more inhospitable place. And so that ozone layer helped protect us. But even if we had an ozone layer, if we had lots more ultraviolet light from a hotter, bigger star, it would be detrimental to life. Another thing that's not on here is that these large stars tend to be metal poor. So they're so hot that they vaporize a lot of the metals in their nebula, and so they don't form planets as well. Poor at forming planets. Now we are finding planets around these giant stars. They're just not as common as planets around smaller stars. All right. Now if we look at low mass stars, this is stars like the sun. Remember the sun is a G-type stars. So these are 97% of stars. They live for billions of years. So there's enough time for life. So these are good. Some of the smallest ones, like the M stars, have very small habitable zones. And so that can be bad if a planet is too close to its star. It can become tidally locked, just like the moon around Earth. And this would be bad because we could have one side of the planet always in sunlight, or starlight, as the case may be. So that would be bad. It might fry that side of the planet. Although if it had a thick atmosphere, it may be able to redistribute some of that heat. Another thing about the lowest size stars, these M ones, they're relatively unstable and can often emit bursts of solar particles. These are called flare stars, so that's bad. Planets could be sterilized by such an event. Remember, these energetic particles can cause cancer here on Earth, and they could destroy life, break up any sort of DNA or whatever mechanism life on that planet has to pass on genetic material. And so those things are bad. So it turns out that the best candidate here for life are G-type stars. And maybe I should say G and K type stars. And they're a little bit like Goldilocks. They're not too big, not too small. So, maybe not surprising, our own sun is one of the best types of stars to find life around. So, yeah, we don't want them too big, we don't want them too small. Those stars at either extreme have problems when it comes to either forming planets or allowing life to form on those planets. All right, the last thing we were going to talk about is binary star systems. So this could also be multiple star systems, anything more than two. We could have 2, 3, 4 stars all orbiting around each other. Now, this may seem like a weird thing to talk about, but it turns out that we think at least 50% of stars are in multiple star systems. So about half of the stars we see out there are really binary, triple, or quaternary systems. And so these are lots and lots of stars. So there's typically two types of orbits we can see down here. So generally, planets will orbit outside of the two inner stars. We can see that here, where the stars are very close together, a very close binary, and the planet here is orbiting around them. More or less, they would act like a single star. These are okay. These give fairly potentially stable orbits, as long as that separation is big. This orbit is often called a p-type circumbinary. Now, the other type is, or the planet might orbit around one star orbiting another. And you see that here below, where we have these two stars orbiting a common center of mass here, and then the planet is going around one of these stars. So that would be potentially a stable orbit. So if we kind of, again, have either one of these extremes, this is called an S-type. Both of these might be okay for stable orbits. Now, if we have something in between, like down here, where the planet orbit is about the same scale as the star orbits, these are unstable. And that would be bad for life. And what that means is that if an unstable orbit means that the planet wouldn't be able to stay there, it would at some point be just ejected out into space and become one of those rogue planets we talked about a few weeks ago. So, these binary systems have the potential for unstable orbits, but what we really need for not just single stars, but or I guess I should say not just for multiple star systems, this is true for single star systems, is we need stable orbits. Maybe I should say stable, nearly circular orbits within the habitable zone. Now, this stability is not just an issue for planets around multiple stars. When we get lots and lots of planets in a solar system, so we've found a few solar systems out there, extra solar systems, that have 8, 10, 12 planets, those can become unstable as the planets interact with one another. Oftentimes, these planets are ejected into space. And we even saw this in a simulation back when we talked about forming our own solar system. I showed you that one simulation of the migration of Uranus, Neptune, Jupiter, and Saturn, and in that simulation there was a fifth giant planet that was ejected from the solar system. So there was maybe unstable orbits in our own solar system as it was forming. So this idea of stability is an important one. All right, so that's all I have for today. Hopefully you got a chance to take the exam over the weekend. I'll try to get those graded as soon as possible. I would like to get them all graded this week so that as we go into finals next week, you all have your grades up to date. All right, well, take care and have a wonderful day.